So in this project, so that's an ACESS project, and the aim of this project is to understand the weakening of the Atlantic overturning circulation to the southern hemisphere, and more specifically to the high latitudes of the southern hemisphere. And for that, what we want to explore in this first study is how those anomalies related to the AMOC or related to the AMOC weakening, they can propagate towards the southern hemisphere, and what would be the impact in the southern hemisphere until it reaches the Southern Ocean eventually. And I'm sorry about starting my talk with this pessimist image, but that's just the reality that we are into right now. So just going to start with some quick introduction of just with some quick introduction of the AMOC. And here on the left, I've just listed many of the climate features that the AMOC can actually impact and can also affect by either strengthening or weakening of the AMOC. But what I really like is this schematic of the AMOC here, because when we think about the AMOC, we usually think about kind of a latitude depth graph. So just this kind of a 2D view of the AMOC going northwards on the surface and then recirculating towards the equator and towards the Southern Ocean at depth. But if we look at kind of a 3D map of the AMOC, there are many other interesting features that we can use to assess the state of the AMOC and can give us some clues of what is going on or with the intensity of the AMOC, especially in the past century, and how it can change into the future. So we all know that all of those surface currents here, they are transporting heat towards the north, but it's no exactly straight path towards the north. So we've got the warm Agulhas current here that comes from the Indian Ocean, and then those currents, they propagate into the North Atlantic as the North Brazil current until reaching the Gulf Stream, and finally ending up in the subpolar gyre, where we've got this, where those warm waters, they lose the heat to the atmosphere and then sink, and going back again at depth as the North Atlantic deep water. So as you can see, there are many features here that we can explore in order to better understand what is going on with the AMOC. And that's what we are going to explore here in this talk and try to assess from those features what is going on, more specifically in the South Atlantic, that can give us some clues about the current state of the AMOC. So first, some background on some of the studies that have tried to assess the state of the AMOC and how the AMOC has been changing in the last century. And most of these studies, they use the North Atlantic to assess the state of the AMOC, especially because this feature, which is a kind of a cold blob or the warming hole, it depends how you want to define it, but which is related to the weakening of the heat transport towards the subpolar gyre. So, and here just by this cooling anomaly or this cooling trend in the subpolar gyre, we've got the warming of the Gulf Stream. So these would indicate that all of the heat that's being transported by those northward flowing currents, it has been converged in the Gulf Stream due to a weakening of the Gulf Stream, which leads to this cooling anomaly in the subpolar gyre. And the study that has tried to access this, so they have created two metrics, one that measures the warming of the Gulf Stream and the other one that measures the cooling of the subpolar gyre. And if you can look at this graph, they are kind of related to one another. But one thing that it's kind of a caveat to look at the North Atlantic is the multi-decadal variability of the North Atlantic, because we do have quite strong decadal variability in the North Atlantic. So when we take into account the Atlantic multi-decadal oscillation or the Atlantic multi-decadal variability, which is defined basically by this spot and here on the right. And if we take this index of the AMO and we compare with the index from this study here, that would be indicating a weakening of the AMOC, we can see that there is a stronger relationship between the AMO and this index that would be indicating a weakening of the AMOC. But we know that the AMOC and the AMV or the AMO, they are intrinsically related, and one can affect the other. So this makes the things slightly more complicated to evaluate the state of the AMOC by looking only into the North Atlantic. So the graphs that I showed you before, they were all related to the observations. And now let's see what the climate models are telling us. So here on the left, we've got several reconstructions of the AMOC, or even direct measurements as the wrapped array. And those red crosses here are also direct measurements from Kansal. Here we've got Frederica Williams, who has obtained some kind of extension of the AMOC measurements based on satellite altimetry. And here, so this blue one, the longest one, it's a kind of an AMOC anomaly derived from the previous SST index. And if we take the trends of those indexes here over 2 periods and compare against the models, there is a weakening period at which those indices here, or those direct measurements of the AMOC, are suggesting between 1957 and 1992, which is not captured by the CMIP5 and CMIP6 models. And then we've got over this observational period of the AMOC at 26 degrees north, we've got this strong weakening between 2004, 2005, and 2015, which was also not captured by the CMIP5 and all the CMIP6 models. But the SST index also failed to capture this weakening that was suggested by the direct measurements. And if we look, and there is this other study, what those authors did was, so they look at it, they try to assess the difference between historical simulations and its models pre-industrial run. So they did a bunch of statistics to try to see if there is any statistical difference between the historical simulation of the AMOC against the pre-industrial control of each one of those models. And they come to the conclusion that for the way that the CMIP5 and CMIP6 protocol and the CMIP forcings, the natural variability has dominated the Atlantic, the AMOC, since the beginning of the past century. So based on this status between, or based on this disagreement between model and data, what we did was, so we tried to reassess those fingerprints, those surface fingerprints of the AMOC, to idealized simulations, to try to understand the process that could lead to some important fingerprints of the AMOC, and if we could extract an important information that would give us some clue of what is going on with the AMOC. So for those idealized simulations, I would just quick jump to the results, so then we can discuss the historical simulations that were performed later with the resources from this working group. So basically, this was the result that we've got from those idealized experiments, and we could come up with a mechanism of how heat and salt is converted into the South Atlantic and eventually into the Southern Ocean. So basically, when we add meltwater into the model, this meltwater displaced the isopycnus in the North Atlantic, and that's what caused the weakening of the AMOC. But at the same time that this meltwater or those isopycnus are displaced here due to the AMOC weakening, what we see in the models, and here we have used two models. We have used the ACCESS-ESM 1.5 and also an ocean-only simulation with the ACCESS-OM2 at the quarter-degree resolution. And those graphs here have been produced using the quarter-degree model. So that's why we can better see some of the features, especially at the boundary currents. So when we've got those displaced isopycnus into in the North Atlantic, some waves are triggered in the ocean, and we could identify a very fast teleconnection between the North and the South Atlantic. So first, there is the Kelvin waves are generated in the subpolar gyre, and they travel along the western coast, the western boundary of the Atlantic, and they cross the equator. And along this path, they modify the bathychronicity of the Gulf Stream and the North Brazil current. So they just weaken the Gulf Stream and the North Brazil current, and that's a very fast weakening. I'll show you some time series in a moment, but these Kelvin waves, though they just reduce the transport of the Gulf Stream and the North Brazil currents within 5 years. We are applying a quite strong meltwater forcing, because those are idealized experiments, and we want to see the AMOC signal into the Southern Hemisphere or into the South Atlantic. And when those Kelvin waves, they reach the eastern side of the Atlantic Ocean, this signal propagates towards the interior of the ocean as Rossby waves. So those Rossby waves, they propagate towards towards South America and towards North America in the North Atlantic. So in the North Atlantic, those Rossby waves, they would constitute a negative feedback to this initial AMOC weakening. So these would be downwelling Rossby waves, which would again try to deepen those isopycnus in the North Atlantic, and they would constitute a kind of an AMOC strengthening. And these occur at multi-decadal to multi-decadal time scale, because that's the time that the Rossby waves takes to propagate from the eastern to the western South Atlantic. And the Rossby waves into the South Atlantic, what they cause is when they reach the western coast of the South Atlantic, they intensify the Brazil current and then also intensify the ACC, but they also cause heat and salt convergence into the western South Atlantic. So here we can see, so for this top panel here is just showing the changes in salinity within 10 years of the model run. So we can see lots of points of convergence of salt along this pathway. So here first in the Gulf Stream, then the North Brazil current, and also in the upwelling regions of the eastern South Atlantic, and finally here in the western South Atlantic. So based on this mechanism, we could develop some new indices for the AMOC. So here first what we took was the eastern side of the South Atlantic, which is this first index here. And here I'm comparing the ACCESS-ESM run with the ACCESS-OM2 at the quarter-degree resolution. And we can see that both models agree quite well. But here for the here for this index in the East and South Atlantic, we have also conducted a salinity budget in all of those regions. And for the East and South Atlantic, the ACCESS-ESM and the OM models, they both cause some convergence in this region, but for different reasons. So the OM better simulate the dynamics of this region. So what we got was that almost 50% was caused by changes in the ocean circulation, and another 50% caused by heat conversions that enhances evaporation. And in the ESM, most of this salinity increase in the East and South Atlantic is caused by enhanced evaporation. But when we go into the West and South Atlantic, where we've got this Rossby signal, and we consider the Kelvin signal, it starts to cool quite fast. So as soon as the AMOC starts to weaken, we can see this Kelvin signal appearing or emerging in the East and South Atlantic. If we go to the West and South Atlantic, then we have both models agreeing quite well on the dynamics, on changes in the dynamics of the ocean circulation that has been causing this salinity signal related to the Rossby wave propagation. And we can see that this Rossby wave, this Rossby signal, it takes a bit longer than the Kelvin signal. So it takes about 15 years to emerge in the West and South Atlantic, and that's the same time scale of the intensification of the Brazil current, and then the intensification of the ACC as well. And both models agree quite well on those time scales, and also on the magnitude of the salinity convergence and the Brazil current intensification in the West and South Atlantic. So we have developed those salinity indices, and we could also add another one that I'll just show in a moment in the next slide, which is an SST index, so an SST-based index, which is going to be the difference between the change in temperature the changing in sea surface temperature in the subpolar gyre, very similar to the index that was previously proposed. But here we are going to also take into account the heat conversions into the South Atlantic, and more specifically here in the Rossby wave signal, which is the strongest signal, and also the signal that is well simulated by the ESM model. So what we did was, when we applied those novel indices to observations, this is what we get. So here on this B panel, I'm showing you the two salinity signals, which is the Rossby and the Kelvin. So the Rossby is just the solid line, and the Kelvin signal is the dashed line. Here I'm excluding those time series here before 1955 because the weights of this data set related to the observations. So the observation weights is quite low, so it's nearly zero. So we can't really take into account anything that has been measured, or anything that is in this data set before this time. But after here, what we see is just in about 1975, we've got the emergence of the Kelvin signal, which is this one here, the dashed line. So there is a significant trend, in a significant increase in trend. Here I have just reversed the y-axis. So a weakening of the index means a salinity convergence, so an enhanced salinity in the South Atlantic. So here we can see that there is this weakening in the Rossby in the Kelvin signal. It's a quite fast one that has been captured at about 1965. And this is in agreement with the later emergence of the Rossby signal. So the Rossby signal starts to emerge at about 20 years later than the Kelvin signal, which is approximately the time scale suggested by the idealized model simulations. But in the idealized model simulation, those time scales are slightly shorter. And we believe that's because of the intensity of the freshwater forcing, because in those idealized simulations, we apply a stronger freshwater forcing in order to identify the signal. And under weaker freshwater forcing, which will be related to this historical period, those signals would take a bit longer to emerge in the observations. And here on this figure on the bottom panel here, I'm just comparing three SST index based on the AMOC. So the blue one is the classical one that I've showed you in the beginning of the presentation. So this one is just based on the code blob. So it's just the SST anomalies in the subpolar gyre, and we can see that there is quite strong variability, and it doesn't really captures any significant trend. Then we've got this the green one, which is the subpolar gyre index corrected by the polar amplified warming, so corrected by polar amplification. So when we accurately corrected this index by the polar amplified warming, then we can see some kind of we can see a significant trend, especially since 1950. And this last one is what we have called the modified SST dipole, because there was a previous SST dipole, and here we have modified this SST dipole index in order to focus on the Rossby wave signal. And when we focus on this Rossby wave signal, it shows a time of emergence of the signal at around 1975. So in agreement with those salinity index that were also based on those waves. So those are two different indexes based on salinity and SST that end up showing some similar results. And the time of emergence here is just a measure of when this time series emerges from this envelope of here of variability, which is associated with some kind of equilibrium variability of the AMOC. And here what we did was, so those shadings here are representing 2 times the standard deviation of the period from 1900 to 1950, which we took as a kind of an equilibrium period. And we can see that, and what this analysis is indicating is that this AMOC awakening signal is captured by this modified SST dipole index and indicates the time of emergence at around 1975. So the previous time series, they were just observations. And now here I'm replotting those observations, but now against the ACCESS-ESM model. So the shading here is representing the 95% confidence interval of those index for the ACCESS-ESM historical simulation. So this is based on the 40 member historical simulations that has been run for the CMIP. So this is just under the CMIP protocol. And we can see that, especially for those indices here, but more specifically for the SST dipole, and more evident for the salinity index based on the Rossby wave, we can see that those simulations, they fail to capture those signals in the South Atlantic. So the observations, they go a bit off this 95% confidence interval. And when we go to the AMOC trends, so here also the red is just observations again, and observations from different from different studies. So here we've got the stars from CANSOL, the red lines, just the recent Raptor array, and the orange line is the satellite altimetry reconstruction for the AMOC. And when we compare those trends, the trends in those indices against the trends from CMIP5, CMIP6 models, and this large ensemble of the ACCESS-NRI 1.5, we can then compute those trends for those two different periods, which is this one from 1957 until 1992 at the second half of the 20th century, and this one here at the beginning of the 21st century. We can see that all of those models or all of those ensembles, they fail to capture those AMOC weakening trends that has been suggested by the observations. So basically, based on this, we hypothesized that this could be this data model disagreement could be related to the absence of freshwater forcing in those simulations. And what we did was we tried to develop a freshwater forcing based on those index in order to capture them and see if this could be related to the freshwater forcing. So we came up with a freshwater experimental design, a freshwater input for these, and those are the results of those simulations. So we have run historical and future scenarios. The future scenario is just a linear decadal step change in the freshwater forcing. And we can see that those historical simulations under freshwater forcing, they can better capture the AMOC trends and also the index, those AMOC indices, because they were based on those indices, but they can also better capture the AMOC trends. And finally here, just one last slide. We just compare the long-term AMOC trend instead of just splitting into two multi-decadal periods. We just compare the long-term AMOC trend from 1957 to 2021. So those are the results for the historical simulations from CMIP5, CMIP6, and the ACCESS-NRI. And they all tend to simulate an AMOC weakening of 0.2 SVEDRUPs per decade, while the observations are suggesting some stronger weakening. And when we add the freshwater forcing based on those evidences from the AMOC indices, we can better capture the AMOC weakening that has been suggested by the observations. And this freshwater forcing that has been applied to this in this historical simulation is within the observational estimates of freshwater forcing from Greenland and from regions around the Arctic. And from this, we concluded that the contribution of multi-water inputs to the recent AMOC weakening, it's about 60%. So those so the CMIP protocol, the current CMIP protocol underestimates the AMOC weakening by approximately 6%. Okay, so I think I have talked a lot over here, almost at the time. So I'll just leave this up here if there's any quick question.
Okay.
I have to take
Thanks very much, Gabriel. Do we have any quick questions for Gabriel at the moment? I suppose.
And I'll just let you know that those simulations are on the around the G data of this working group. So if anyone is interested in looking at those simulations or analyzing all the process or whatever you want to do with those simulations, they are available for everyone within this group.
Okay. Can I just ask some details of the meltwater forcing? Was it like a fixed value every year, or did it gradually ramp up? I remember it being kind of based on the observations, so I just don't remember the exact details.
Yeah, so I didn't have time to go through the exact details. So so basically what we did was, for the historical simulation, we did a kind of a constant low, kind of constant weak freshwater forcing from 1960 until 1990, and then we do a kind of a step change increase, but those are from decadal step change increases after this constant from 1950 to 1990. Yeah.
Okay. Yeah, it's really interesting. I haven't seen the rapid measurements for probably the last 5 years, and I can recall, there's that rebound that you can see in the time series, and then it kind of plateaus again and kind of starts going down. So it's kind of really interesting watching that kind of play out. Siobhan, you have a quick question?
Well, it's just two questions. One was the actual physical pattern of that forcing, and I mean, how did it fit around Greenland in terms of where it was? And as you said, you also had some from the Arctic itself, from the Arctic rivers. You also look like you switched it off and then switched it back on again around the year 2000. So is that what actually happened? Or, you said you took it from 1960 to 1990 and then switch it on. But it was a very interesting talk. I was just looking, there was so much detail in it. It was just difficult to follow it all.
It was quite a lot of information. I didn't realize that when I was just making this presentation. But just to answer your first question, so the location of the freshwater forcing, we just put around the southern tip of Greenland, and also extending towards the Canadian Arctic. Because the observational studies, they suggested that most of the freshwater flux they come from either Greenland or the Canadian Arctic. So that was just to capture this region. And that's just your second question. We do switch off this the forcing from 1990 to 2000, and that was based on the observations, because the observations suggested some kind of no warming during this decade in Greenland, and also some very small changes in the sea ice extent. So we proposed that over this time, the freshwater forcing could be rather small, and we could just neglect it in order to perform some kind of simple experiment.
Okay, it was just that after year 2000, the melt just really jumped up in Greenland. That was why I was thinking. I mean, yeah, I can't remember what happened in the 1990s, but after the year 2000, the melt just really jumped up. So yeah.
Yeah, so that's why
basing on observations, that's fine.
Yeah, so that's why after 2000 we do some kind of very quick step changes here in order to capture this very fast increase in the freshwater forcing.
Yeah, it's been a really interesting talk. I'm glad it's recorded so we can see it again.
All right, thank you very much for the talk, Gabriel.